Is that yours or? Okay. All right, welcome back, everybody. We're gonna get started on lecture 4. So we're kind of going, bottom up. We did some chemistry, physics, masks, and layout. We're gonna get up into devices and CMOS. And I do owe. I'm gonna do a demo today. I'm gonna actually save it till kind of halfway through, just when I see people starting to nod off. Then I'll be like, hey, we're gonna do a demo. So I'm going to aim for like 1:15-ish. I'll see where it kind of pauses halfway through, though. But again, I talk about there's these tutorials here. I'm going to look through some of the files in that the tutorials for K layout, and some of that's useful on your homework 1. Homework 2. Homework 1 is mostly review stuff, and homework 2, Hodder posted yesterday. That has some more questions on recognizing some layout and things like that. So now, the rest of the lecture, though, we're going to talk a little bit about semiconductor devices. So again, like the other stuff, there's entire fields on this area, but I'm trying to explain kind of the mile-high understanding of the topic, especially what relates to you as a digital designer. We're going to talk a little bit about diodes. We're going to talk about field effect transistors. We're going to talk about FETs and their characteristics, like the width, length, the on resistance, body connection of transistors, and then parasitic resistance and capacitance. The review stuff, I may hit a slide or two on this, but you should have seen this stuff in some places, and I'll kind of talk a little bit more about it again. Someone asked me, do I cover everything in lecture for the homeworks? Pretty much. Again, I have those readings in the textbooks that go beyond what I talk about, and there's some review stuff in homework 1, but other than that, you should be able to do most of the homeworks by the time I get done with the relevant lecture. So they're kind of, when you get the homework initially, you may look at a couple problems and be like, I don't know anything about this, but in the next couple weeks before the due date, you will see that I cover some of the material. So now, this weekend I was actually looking through and I found this interesting quote according to ChatGPT. Albert Einstein actually said that genius is 1% inspiration and 99% working on your homework on your own. Wow. If I hadn't done my homework, E would have probably still equaled MC cubed. And the universe would be a very crowded place. So this makes a few points. Again, do your homework. Work on it through yourself, through the process, and ChatGPT can be wrong. Okay? So, again, every lecture I'm going to show you this slide. All right. Now, question back here.
Question going back to the homework. You said you were going to release answers on the homework. Is that going to include kind of working through the problem or just straight answers?
Yeah, when I release the solutions, it's usually going to show the work. So that's why I'm not going to release them. I was debating on it because I was talking to some of my colleagues that actually release it like an hour before the deadline so you can then check your solutions and fix it and so on. But again, I'm grading the homeworks for kind of, did you try the problem? Did you make an effort? If you did it the wrong way, you'll learn. If you made numerical errors, you'll figure it out with the solutions. I'm not going to do that because I have it due at midnight, I think. So I'm not going to release it at 11 p.m. and make people look at it at 11 p.m. Again, I want to see that you've worked through this stuff on your own, and my intent is that you submit things that you did by yourself. You're not supposed to plagiarize, but once you do it, you are more than welcome to talk to other people, look at my solutions, ask ChatGPT. I don't care. But I want to see you kind of work through it on your own. And so I'm trying to lower the bar there so that people don't worry about, oh, do I have it exactly right? Because what you end up having is people that just copy things and they don't understand it. And they might get credit, and we don't know if they did it on their own. And I'll be able to tell, yeah, I'll leave it at that. So again, it's a different way I've taught this class than before, but it's something I'm trying. I'll tell you my worries. I'll be completely honest. I'm worried that people are not going to do this. We're going to do the first midterm, and people are going to do very poorly. Some people will. I can guarantee it. But if you do this, you will do okay. You'll do great, actually. If you go through those homeworks and you know how to do them, you'll do fine. So that's why it's the key to how to do well in the class. Because I actually gave you 20% for the homeworks, which actually is probably high. I probably should have said 10%. But 20% of your grade is free, right? But what that means is there may not be a curve as much on the other part, because there's going to be less kind of distribution of grades. I'm not saying there won't be a curve. There probably will be a curve, but and the exams will be challenging because some people won't have done the homework, and so the means will generally be pretty low. I can guarantee that's just human nature. That's the way it comes out in these classes. Yeah, question. Oh yeah, that's actually a good announcement. Midterm, I actually have a second room for the midterm, so we're actually going to split into 2 groups. And I'll announce that ahead of time. I was able to secure a second room that's over in Baskin. So we'll be roughly half and half. Yeah, I was worried about people elbow to elbow, and so this will get rid of that problem. And I'll give people plenty of notice which room they're in. And we'll also take attendance to make sure you're in the right room. Okay. Actually, we'll know which room you're in because of which room you turn the exam in. So we don't have to take attendance. Okay, so materials. We're going to start from kind of the fundamental level. You know some of the actual chemical compounds. We've talked about you have conductors like aluminum in the blue up here, or copper. We talked about silicon dioxide, which is an insulator. We talked about P and N-type semiconductor, if it's doped with P-type material or N-type material. Yeah.
What's the symbol across the N supposed to represent?
Symbol across the N.
Like PN junction. So why is the N marked like that?
Marked like what? Which one?
A dash.
Oh, this?
No. In like the literal word cross section of PN junction. Yeah, caption.
Cross section. Oh, that's just a font error. It's supposed to be PN-junction.
Okay.
Yeah, that's every year you use any of these like things, they mangle fonts. Google, Apple, Windows, PowerPoint's horrible. So anyhow, yeah, that's a good question. It's PN-junction. So yeah, you have these materials, right? Metal, silicon dioxide. This is all silicon, but this is the P-type, which means it had holes more than standard silicon, and N-type, which had the electrons. And we saw before how we could process all this stuff, right? Like, how could we make, as a review, how could we make this P-type material in the N-type substrate? Yeah, you want to make a well, so you either use one of 2 steps. One is you let the dopant diffuse into it, or 2, you implant the dopant into the substrate. And you can do that to form that. And then you can grow the oxide on top of here to insulate it. You can do what step to get these holes here? Etching. Yeah, so you etch the holes in here, and then you deposit your metal, then you etch away where you don't want your metal, so that you're left with those contacts, the A and B terminal. Now, if we look at kind of the cross section, the dotted dashed line, you're going to see basically a sandwich, kind of like down here of these materials. Oops, let me get rid of that one. Like this, where you have the A terminal is connected to some P material, which then is connected to some N material, and then B. But notice this kind of junction right here is not actually flat. If you look up here, it actually consists of this entire kind of almost rectilinear region right there. And no, also it's coming in and out of the board because it's going to have a physical area if you look at it from the top view. Actually, from the top view, that'd probably be a useful example. What would the layout of this look like? Well, if we just kind of, not to scale, but if we draw it like this, there's going to basically be two contacts like this for the holes. There's going to be some metal around those like this. And then how did we do that P-well? Well, there's probably going to be a P-well layer that we draw like this. Right? And then if we do the cross section of this, it'd be through kind of the middle of that. Kind of dash, 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 dash. So that's what the layout of that would look like. Now, and then this is represented by the symbol you've probably seen before, a diode on the right. So how many people know how a diode works, roughly? Right? Kind of, if the voltage on A is bigger than some by B by some amount, which is called the on voltage of the diode, it connects A to B. However, if A is not greater than B by that amount, it's off and it's essentially disconnected. So it's kind of like a switch, but it's not a MOSFET. They used to have to make a lot of things out of diodes, right? You still use them for power rectifiers, ESD protection. If you on the IOs of the chip, if you touch it, it'll be a really high voltage. There'll typically be an ESD diode that discharges when you shuffle your feet and shock the chip to get rid of the charge. So they're still used on chip, but just not usually for logic. But you can make them on every chip. Now, how do these behave? Scary equations. You do not need to know these equations. I will put that there. Don't need to know. But why do I put them there? Why I put them there is that it's actually, they derive a voltage that's actually pretty well known, you've probably seen before. And that voltage is down here. You can see about 600, 700 millivolts. That's usually the on voltage of a diode. Somewhere between that and like 1 volt, 1.2 volts. You can actually control it, but kind of with standard P and N type, it's about 600 millivolts. Why is that? And that kind of will give you an intuition of how a diode works in terms of semiconductors. So remember, if we have P-type material and N-type material, we can add impurities. And what that means is we have these extra carriers, right? You either have electrons that kind of drift around because there's an extra electron, or you have holes that drift around because there's one too few electrons. Now, we're going to draw those as, negatives for the electrons and pluses for the holes, okay? Now, there's two forces that act simultaneously when you have a P and N type together. And these are going to be the diffusion force and then the drift force. Now, what is diffusion? Well, now, by the way, this is all solid state physics, is what they call it. It's how you make devices, how the semiconductors work. They get into making lasers and things like that out of this stuff. It's an interesting field, but obviously beyond digital design. And so, what are these two forces? Well, diffusion is when you want to go from a high concentration to a low concentration. So this is you have a coffee cup, you put creamer in it, and your creamer is going to want to diffuse throughout the coffee so that you have even distribution of creamer. Things like to go to a steady state where everything is even. So you're going to have that in this case. N-type has extra electrons. So what are they going to do? They're going to like to diffuse out of the N-type away from things. P-type has extra holes. What's going to happen to the holes? They're going to try to diffuse away from the P-type to kind of even out. So That's this top forces right here, the diffusion forces. Now, you then also have electrical kind of behavior where you're going to have drift where things are going to simultaneously attract to the other types. So if you suddenly have extra positive charges on the right, those negative charges are going to want to be pulled towards the positive. And then the positive charges are going to want to be pulled towards the negative. And so you're going to have this counteracting force to the concentration. And so what happens is these then find a balance. They hit an equilibrium. And what happens is when they're in equilibrium, you have these kind of areas of, there's definitely a p-type, there's definitely an n-type, there's what's referred to frequently as the depletion region or a diffusion region in the middle of this thing where there's actually a gradient of kind of the concentrations of electrons and holes. And the concentration actually kind of, looks, if you look at the concentration on a chart, it looks kind of like this for one, and then the other one goes up like this. Something like that. Now, when we do this, the P is electrically isolated from the N. They're not conducting, but they're in this equilibrium. And you can think of that space where you have these concentrations as basically a disconnect, right? Because once you have a concentration below a certain amount, it's essentially not conducting. But what you can do is you can apply, and there's a couple terms over here, right? These equations use Na, Nd, and Ni. Ni is essentially the intrinsic concentration of carriers in a semiconductor. So if you have pure silicon, if it's not at absolute zero, so it's at, say, room temperature, there's going to be some motion of electrons and holes, just based on it being silicon, and it's not a perfect lattice that's like holding these in place all the time. But then when you add these dopants, you're going to add them in the concentration of either Na or Nd. So this is you created, you had either this N-type substrate with a concentration, and then you injected the P-type in with a dopant, and that has a concentration. That's Na and Nd. So depending on those concentrations, this kind of weird log normal function, it's natural log of the ratio of the product of these two to the intrinsic. This gives you a voltage here, which is the workforce difference between these. And then it's related to, that is essentially, these are common values. It gets you, this 10 to the 16 and 10 to the 20, this is standard silicon, and then these are common dopant concentrations for P and N type. That's how you get that voltage. You can change this type, how much dopant is here, to somewhat adjust that. If I add different concentrations and say make them have higher concentration, it'll give me a larger voltage. If I add lower concentrations of P and N, it'll give me a lower voltage. So that's why I can make a diode with a 1.1 volt on voltage by changing these concentrations. That's all they do. That's a diode. It's actually kind of simple from a high level, right? High level, mile high view. Now, how do you turn it on? Well, what happens is you're going to apply a voltage to this thing. And so again here, on VD, this is the voltage across the diode. So look at this left one first. And so if we have 0 in the middle here, this is kind of that state where nothing's connected. It's off. We know that there's that stuff going on in that middle region. But then when you hit that voltage over here, that 0.638 volts or 638 millivolts, it's going to turn on. Because what happens is you have the drift current, which is basically the natural charge wanting to go towards the opposite carriers. But if you apply a voltage, you're essentially augmenting that drift that drift by applying a voltage to this and saying, the voltage causes electrons to flow or holes to go the opposite direction. So you're applying that voltage, which essentially counteracts that natural balance of diffusion and drift and will push the regions together so that you effectively turn it on at some point. So you kind of squeeze them down until there's the drift plus your applied voltage dominates the diffusion, and then it's on. And then P and N conduct, and you can see that the voltage or the current through this thing skyrockets right here once you hit that voltage. Now, if you apply a negative voltage, it basically just doesn't do anything. It makes that region wider, but it doesn't really affect the current that goes through that diode very much. You may observe, who's heard of like a Zener diode? That's another special case where you can actually have a case of reverse breakdown where you might see something like this over here. Where if you apply enough of a negative voltage, it'll essentially go on in the opposite direction. But that's another thing. Now, I said that this region over here is essentially flat, but it's not quite. This over here is kind of that region. This is 0 to 6 volts. But you can see if you plot this on a logarithmic scale, so this is exponential because it turns into a line when you make this axis exponential. And you can see that because a line that's exponential, but then this still has a line, but it's a slightly different angle. And so that's called typically the sub-threshold slope, or kind of below when you're on. It still modulates the current a little bit, but the current's very small. And this is also called the leakage current of a diode. So it's not perfect. So it's not, when you forward bias, it's on, but when it's not forward biased, it's not perfectly off, it's mostly off. You still have a little bit of this current that sneaks through, and that can actually cause problems like power consumption in chips. That is frequently referred to leakage current in chips, and it's one of the most dominant components of power consumption. Because if you think about it, we're not going to make diodes directly, but there's going to be a bunch of diodes on a chip when we make transistors that all those diodes are going to be leaking kind of in parallel. Like if you have, 8 billion transistors on a chip and they all leak a little bit, well, it's 8 billion times a little bit, which is a lot. And so you have to do tricks to reduce this when you do design. Now, another thing is it's also related to temperature quite a bit. This is the standard diode equation you have probably seen in textbooks, which relates the voltage here, which is across the diode, to that essentially the on voltage of the diode. And then this IS term actually depends on the area. Because if we go back to when I showed the layout here, where does the current flow through this thing? Well, if we look at this sandwich here, it's going to flow let me turn it into drawing. It's going to flow all in this area. And so what happens is, depending on how big that area is, it's going to change how much current can go through it. So that's that IS term. It's dependent on the shape and the size of the diode you make. If I draw a bigger rectangle here, I'm going to have a bigger diode. If I draw a small rectangle of the green, I'm going to have a smaller diode. And so that changes the total amount of current, but it doesn't change the voltage to turn it on. Now, we're going to not really design with diodes, but it comes into play later. We're going to stick with the switch model of a transistor with a resistive kind of first order component when it's on. And that's not because of diode resistance. But again, we're going to show why it matters. So I showed this before. I mentioned if you have the voltage across between the gate, this is usually VG, this is VS, this is VD. So if you have a voltage difference in this case between VG and VS, where VG is greater than VS by a threshold voltage. So this is shorthand. Usually VGS equals VG minus VS. This is basically just a shorthand notation. Okay. So if VG minus VS is less than the threshold voltage, this thing's off. And if it's greater than that, it's on. This is a different threshold voltage than the diode, though. I want to make sure I keep saying that. So how does the threshold voltage in a transistor differ? Well, I started to get to it last time, but we now have typically a P-type material substrate, right? And then we did implantation to make the source and the drain with the N plus material, right? So if we draw it in green, we had N plus here, N plus here. And in between that is just without any charge or without any voltage, there'd be P substrate between here too. right? So I've kind of drew in this depletion region and this channel region, but this is applying a voltage. So without that, there's nothing here, and it's just P, and you end up having N, P material, and N. Well, what do we say N and P together make? Diodes. So what do we have here? Well, P and N. There's a diode here. P and N. There's a diode there. We're not using that, but that's a side effect of making the source and drain of the transistor. What happens if you raise this voltage here of this substrate up above the voltage of this? It would forward bias, and you'd have current go from here to here. You don't want that. Almost always, this P substrate is ground. And usually when you use a transistor, often the source or drain will also be ground. In an NMOS, it's often ground, right? You connect the NMOS to ground on the bottom. So this is ground. So usually one of the sides you have P to N, 0 voltage difference, no forward bias. Now what happens if you happen to have a voltage over here? Right here it's showing it as ground. What if you had a positive voltage there? Well, what would P to N be? It'd be negative voltage. It'd be really off. That's good. Because, it would be bad if it was switched around and this is P and this is N, because that would be forward bias. But since this is the N and this is less than that, it's reverse biased and it's going to be off. Yes?
So like in the black, is that like N minus channel?
So I'll get into what this channel is in a second. I should probably put in another picture without any of that stuff. Now, what happens though then is if we assume that we have all of these, this is ground, this is ground, this is ground, and we apply a positive voltage to this G terminal, VG, we end up with a VGS that's, say, greater than VT. Oops. Well, what that does is, in this region down here, remember, like charges repel each other. And so if you apply electrons there, it's going to force electrons out of this region. Actually, in this case, if you apply, I always kind of swap back and forth because physics people and electrical engineering people change the definition of current. If you're talking about current by a physicist, they're talking about the actual electrons. But electrical engineers talk about the inverse, the opposite of that. And so, but anyways, so just kind of stay with the high level idea. So if you apply a voltage here, it's going to repel the same type of carrier here. And if you apply enough of a voltage, it's going to cause enough of a field across this that it repels those and gets rid of them all in that silicon. So it might be P-type, but in this case, if you apply enough of it, it's going to make that essentially into N-type. It'll get rid of all of the holes, turn it into N-type, and then you have N plus an N channel that's caused by this repulsion of all the carriers in an N. And so things can conduct through here. Now, you're also going to see this region around the N and the P. Because it's a diode, there's this depletion region where it's that kind of middle region of the diode, right? So that's drawn in there. Now, why is that important? Well, this channel typically, it affects the size of this channel and kind of how it behaves a little bit. So this is kind of the mile high of how this threshold voltage can electrically change the channel behavior and cause current to flow. But in this case, since VS and VD are both at ground, there's not going to be any current. They're at the same potential. Current doesn't want to go either way. Now, this is where I talk about the modes of operation in this class. The reason I want to show them, I'm not going to necessarily test on the equations for them. This is one of the things I've dropped over the years. I wish that people in EE 100 would actually teach this stuff, but instead they get into phasors and all this other stuff, which is kind of useless for digital designers. A lot of other schools, they teach these equations at the end of EE 101. And this is one of the examples of when you go to job interviews, if you're in a VLSI position, they will probably interview on some of these what we call square law equations. again, we just have basically a few slides in this lecture to make sure you're aware of them, and then that's probably the biggest void in your computer engineering education. I will tell you that right now. Like I actually took an entire class on this, but you guys have classes now in ML and all these other things. There's so many things to study, you have to drop something. So ends up being two modes of operation of a transistor. One is kind of what I was just describing, where we apply a voltage to G relative to S, but we have to look at this other voltage relation, which is the relation of the voltage between VD and VS. So this previous diagram, they were both ground, so there's no voltage difference. VDS, the difference of those is 0, right? So this is, so in this case, because of both of these together, this means the current, ID, equals roughly 0. Even though it's on, it's 0. So it's a closed switch, no electricity flows through it. Here, we're going to add a small voltage to the D terminal, but we're going to keep S as ground. So think about this as an NMOS, where the bottom's connected to ground, like you typically see in CMOS. Then the top has a voltage which you're pulling down. It might be the output of your gate. Now you apply this voltage, this channel forms. As long as this VDS is less than this value, VGS minus VT, we're going to be in what's called the linear region. Now, why is it this case? Well, VGS minus VT is essentially how many, it relates to the kind of the shape of this channel. And if you look here, it's kind of drawn as a rectangular region. It's roughly the same depth from the source to the drain. And what that means is you can think of it as kind of like a hose or a tube or a conduit where the current can flow through that thing that's the same size all the way through the channel region. And that's good because in this region, if you basically apply that voltage, you're going to get some current that is predictable. It essentially behaves in this region kind of like a resistor. And if you know Ohm's law, you know V equals IR. It kind of behaves that way as R. And that R is determined by the shape of that channel, right? When we'll talk more about interconnect too, but if you think about it, if you have a hose and you can push water through a hose, the amount of water that goes through the hose depends on the size of the hose. If you have a very narrow size hose, less water will flow through unless you push it really hard, but then you have to have a lot of pressure to make it flow through. That's because that narrow hose has a lot of resistance, right? But if you have like the water main going down the bottom of the street, it's a very wide pipe, and it will have a lot of water flow easily because it has such a big diameter. That's a similar thing to this channel region, right? If you end up having a big channel, either with a higher voltage, or if you change this dimension in and out of the board, you can make it a very wide pipe. And that can change the current. And it effectively changes R. That's why, to a first order, we're going to use this resistor R on. But that's not quite what we're going to use the resistance as for that kind of linear mode ideal transistor. Why? Well, if we end up having the voltage be too big, the transistor is going to enter what's called saturation region. And what happens here,
What does VT represent?
that's the threshold voltage. That's a good question. Different people call it different things. I've already referred to it in a number of ways. I kind of referred to the workforce. Sometimes it's VTH. Sometimes it's VT. It depends if it's a physics person, an electrical engineering person, or, and normally I like to use VTH as a digital designer because VT can also be something called the thermal voltage, which is more related to the diodes. But for the most part, I'm going to kind of use these interchangeably in our course. Yeah, excellent question. And so in this case, there's this relationship here where if VDS, so the voltage across this channel, or from one end of the pipe to another, it gets too big, you're trying to fit too much current or too much water into the pipe. And what happens? Well, you can't do it very well. And how is that limited? Well, it's limited by the size of the pipe. In our case, what determines the size of the pipe? Well, it's the voltage on G. If we apply more of a voltage, it makes that channel deeper and makes it bigger and essentially makes a wider pipe. So that's why there's this relationship of VDS to VGS minus VT. Why VT? VT is the amount to turn it on. And once you get above that level, it's related to VG. Right? So you turn it on, then you have the relation between VDS and VGS. As long as it's greater, you have kind of a uniform linear distribution. But if you then have too much voltage across it, it starts to distort this channel where it kind of biases it so it's no longer this nice uniform thing. You know, honestly, I hope that this kind of makes sense, right? I think the water analogy is very important, where now you're selecting the diameter of your tube dynamically and putting water through it. When I took this class, I had a dedicated class, but I had a guy that basically had a spreadsheet for everything. Actually, it wasn't a spreadsheet, but we used spreadsheets then, but he used printouts of spreadsheets on foils. And he'd be like, well, what mode is this transistor in? Saturation. Let's get out my saturation spreadsheet and fill in the tables. He didn't give us an intuition into what's going on. He just focused on the equations. What are the equations? They're a little nasty, but they're actually not that bad. I know there's a lot of symbols here. If you learn one thing, I'm not going to test you on these directly again. I'll repeat that a number of times. But if you go for a job interview, I think you should kind of read the section on this in the book. I think it's important to have a little bit of understanding. From a high level, there's certain relationships that I will test you on in these because they're intuitive. Now, what are those? Well, we have the two modes we just talked about. And the stuff I'm going to hold you definitely accountable for is going to be especially this coefficient here. This is the physical dimensions of the transistor. Remember, like we said, if you change the size of the area of the diode, it changes how much current goes through. Well, the same thing happens here. What are the dimensions here? Well, into and out of the board, actually, how do I draw this? If I do in and out of the board, this is W. And if I draw this way, this is L. So width and length of the transistor. Now, I can also draw these. If I draw the top level layout of this, it also makes sense. Let me see. Remember again, we have diffusion, and I'm using the same colors, polysilicon. What is the width and the length? Well, the width is going to be this dimension, and the length is going to be this dimension. Go back to the pipe analogy. The width is how the circumference of your pipe. The length is essentially how long your pipe is, how long your tube is. And it kind of makes sense here, right? If the source is further from the drain, it's longer. Current has to flow longer underneath the poly gate to get to the other end, length. Coming in and out of this thing, if you have a source and drain, there's more essentially parallel connection between the source and the drain, more distance, and so more current can flow through it. So that's why it's kind of the width of this thing. So it kind of makes sense then that width means increased current. If it's wider, more can flow through it. Length means less current. If it's longer, it means you have to push it harder for the current to go underneath the gate all the way to the other end. So that relationship intuitively should make sense. And you should always remember, current is proportional to W over L. Yeah, so then L means current goes down. Now, what is all this other stuff? Well, that's essentially modeling the shape of that channel region, right? It depends on VGS and VDS. And as long as you're in that region, there's a mild dependence where it's roughly linear. And I'll show you a plot of this coming up. You may say, oh, why is it linear? There's a quadratic component at the end of that, but it's largely dominated by if VGS VDS is much less than VGS. It's pretty much dominated by the VGS term, essentially. So it's roughly linear. Not quite, roughly. But then when you hit the saturation mode, what happens is it kind of hits a peak, and we basically take this equation up here, and we just substitute VDS equals VGS minus VT. Remember, for this mode, VDS is greater than VGS minus VT, but we kind of cap that limit. We just substitute it. These two are equivalent if you do that, plus this extra term right here. If you ignore that, that equation and this equation are exactly the same if you do this substitution and solve it. So it's really only one equation. But yeah, then these other things, and there's a half here, I guess. But that's because you have a squared term. So now what is this term here? This is the channel length modulation. So remember that region under the thing kind of distorts depending on the voltage across VDS. And so this is a linear model of that. It kind of just like I drew it, it's modeling it as, instead of a rectangle, you model the slope of this thing, right? This right here, this point changes linearly depending on VDS and that lambda term. And you just kind of move it depending on the voltage. And then you can approximate how much current goes through. Now you may ask, oh, is there current actually flowing under here? Yes. It's just a very thin channel region where some current is able to kind of jump from the D to that point, but it just goes down a lot. And so you're essentially modeling with that extra channel modulation term here what the shape is of that thing. Now, what are these other terms, this K term? Again, this is going to be, called the process transconductance. And what this does is it relates how putting a voltage on the gate affects the channel underneath. And what are the terms that affect that? Well, one right here is the distance from the gate to the channel. Right? If we go back here, that is this term right here, TOX. The further the gate or the polysilicon is away from it, the less the field can control the channel. Right? It moves it further away, it gets harder to control. Yeah.
Wait, what do you say K was again?
This is one term that kind of groups together all these things. It's called the process transconductance.
Wait, then what is the dielectric constant then?
I'll get to that right now. And so then, the TOX is how far away that poly is. And then what do you have in the material between the polysilicon and the channel? Well, this is all silicon dioxide. And it's an insulator, but the field across that depends on the permeability of the dielectric constant. So what type of oxide is it? And so on. Yes?
So I'm kind of confused. The width and the length are perpendicular to each other, or they're parallel with each other?
The width and the length are perpendicular to each other. Yes. Think of it this way. The width is perpendicular to the flow of the current. And the length is in the direction of the flow of the current. Just like a hose. So then this other one right here, this right here is the dielectric for oxide. And so what do we mean by dielectric? It's like how well it insulates and how well it can permeate with an electric field through it. So if it's more insulating, then the voltage will have to be stronger to form the channel. If it's less insulating, it'll be able to control the channel better. So it depends on the distance, the height of that channel, and the material in that. And then this last term is the mobility of the carrier. And what is the carrier? That's electrons. And it's essentially saying how well do electrons move in silicon. So if I apply a voltage to the gate, it causes an electric field and wants to move the electrons out of underneath. How easily do they get displaced in the silicon? or how well do they flow? Because they have to flow out of the channel to get out of the way to form the channel. So all those together form this kind of component, which is related to the current in the device. And it's the same in the bottom down here. So again, it's kind of these mechanical, physical dimensions, the materials, as well as the electric fields and the voltages. Yes?
How do you determine the mobility of the electrons? Is there like a value?
Yeah, so the mobility of the electrons and holes are essentially a constant, but it does depend a little bit on the temperature. If it's higher temperature, things will actually get more resistive because they jump around more and it can impede things from flowing. It can also change a little bit with doping. If they get highly doped, you'll actually have actually that's a good question. Usually this is just intrinsic. I'm not going to guess the second order effects. I started to say that if you highly dope it, it will actually become less mobility, but I'm actually not sure if it's more mobility. If you think about it, if you try to have electrons go through something that has a lot of impurity atoms, it's probably hindered more. So it'll probably be obstructed more and have lower mobility if it's doped more.
So there is some sort of threshold for the
Yeah.
as you dope more.
Yeah. There's going to be these secondary relationships, which I don't know all of them. But in general, the mobility of the electrons, so mu n, this is useful, is roughly equal to 3 times the mobility of p, holes. This is an important thing. Why is it important? We've been talking about NMOS devices and electrons going through the channel. They're going to be 3 times faster, essentially, flowing through and being able to displace to make the channel than holes, which means NMOS transistors are 2 to 3x better than PMOS transistors. If you have the same size, the NMOS will be 3x the current than the PMOS. That's a huge difference. If you're given an option, use an NMOS. They're just much more efficient per unit size. Yeah?
So then when you use NMOS and PMOS in like a complementary manner, how does that affect how you put them
Yeah.
together?
Good question. So if you have a complementary NMOS, let's say just take an inverter, simple case. What do you have with an inverter? If the NMOS is 3 times faster than the PMOS, what do you think you'd probably do with the PMOS? Well, what if you just make them the same size? What will happen? When you pull down, the NMOS is going to discharge the output. It's going to be some delay. When the PMOS has to do it, it's going to have 3x the 1/3 the current, or 3x the resistance. It's going to be slower. And so your pull up, your rise time out of the inverter is going to be 3 times slower than your pull down time. What can you play with as a designer? I mentioned it right here. Width. If you make the width of the PMOS 3 times bigger than the width of the NMOS, you can counteract this. So now you have a 3 times bigger PMOS than the NMOS, but it's going to be balanced. Your rise and fall will be roughly the same. You can see why in this equation. I designed with W. I can't change mu n. And so I changed it to compensate. That's actually going to carry through a lot of our CMOS stuff. When you design more complex CMOS gates, you have to think about this when you design them and how you pick the sizes of the transistors. Yeah.
So that's when they're balanced, though. Is there any applications to when you don't want them to be balanced?
That's a good question. That's how you can balance them. Do you always want them balanced? The answer is no. My boss, when I was at IBM for my first job in grad school, actually had a paper on exactly this question. And if you think about it, when you have a chain of logic gates, say a bunch of inverters or say something computing, how many rises and falls? You're dominated by either a rise path, and then CMOS is usually inverting logic, right? So you have a inverting, inverting, inverting. So a rise will then be a fall in the next stage, then a rise in the next stage, and a fall in the next stage. So any path through this logic is going to have the same number of rises as falls. And so then the question is, if you make them perfectly equal, that makes the both paths equal, a rising input and a falling input. But you can actually make it so that you can speed up all of the falling paths, every other one, and make it faster than every other rising path and use less total size of transistors to get the same delay. And so he kind of did some stuff where it's actually not 3x, you might want to do it more like 2x. Yeah.
Sorry, I missed it. What is the Mn equals the 3 micro?
This is the mobility of the electrons. So this Mn, mun. And if we have these same, I kind of skipped this. If you have these same equations for PMOS, you're going to replace this with mu p. Because now you have the different type of carrier, the PMOS devices, in a different constant. And you'll have Kp.
And then 3 micro, what's the P? The 3.
This is mu p. So this is if you made the mobility of the PMOS, the holes. And this is the mobility of the electrons. This constant is roughly 3x that constant. Yeah, I skipped over PMOS. This is an NMOS. Every textbook you find will skip over PMOS. Why? Well, they're symmetric. The difference is polarities. If you flip polarities, you're talking about holes, so then your currents all go in the different directions, and your voltages are opposite. You need a negative voltage to turn on a PMOS relative to the source. Where here we're talking about a positive voltage relative to the source to turn on an NMOS. And so I'm going to also do that and kind of skip over the PMOS. So I'm going to show this, and then I'm going to do the demo for layup, because I think this was a good concept. This will wrap it together, and then we can do that. So I mentioned that in linear mode, it's resistive, but then we saturate. Well, what does that plot look like? Well, we can see here, this x-axis on the right is the voltage across VDS, a transistor. And this is for one value of VGS. So this is VGS equals VDD. So we're applying the supply voltage on the gate, and we just change the VD voltage relative to the VS. And what we see is, up until a certain point, below, where are we going to have it? Remember, at VGS equals VDS minus VT is going to be some point here, maybe around here. Actually, I'm going to draw it a little bit different. Like say over here, this is basically linear, right? You can see it's almost a perfect line. But then we hit that point where it enters this saturation mode, and then the current kind of hits a limit, and there's an asymptote essentially. And so that linear mode then hits an asymptote, and we can't really get too much above this saturation voltage, or the saturation current. So it's kind of a combination of those two equations here. To the left of that point is the linear equation, and then to the right of the point is the saturation equation. Now, you can use those equations. They're a little cumbersome to do by hand. Obviously, people would have you do circuit problems with them at kind of a couple transistor level. You can use SPICE. SPICE will actually use equations that are even more accurate than those. Those are called square law, which there's a bunch of second order effects when you get into like FinFETs and all these things that make them even more complicated. But SPICE has model parameters for all that stuff. What do we do instead? Well, I want to use this model on the left. And so what resistance do we want to use in that? Well, what operating region do we normally use when we have a transistor? Well, we're going to have the inputs are going to either be VDD or ground. So either VDD or 0. So that's why VGS equals VDD, good choice. What voltage of VDS do we typically see in a transistor? Well, think about an inverter. We have an inverter with the PMOS or the NMOS and the pull down. If the input's a 0, the output's going to be VDD. So we're going to have VDS equals VDD. So we're way over here. Now what happens if we have a 1 on the input or a VDD on the input of the inverter? The output's going to be 0. What is VDS? It's going to be 0 volts over here. Typically, in digital logic, we're going to be operating here and here. What happens when you switch between them? you basically start at VDD, it's going to discharge it, it's going to slowly decrease, and then we're going to come over here. If we then switch the value, it's going to charge up, and current's going to start out, increase really quickly, then saturate, and then charge it up to here and stop. So it's important when we talk about the dynamic behavior of this, switching between VDD and ground. And so for that reason, we come up with this value of R on that's kind of an average of that region. We actually usually average 2 points. One is VDD over 2 and one's VDD. So it gives us kind of that region of the left and right part of the saturation region, roughly. And what you do there is, remember, resistance, Ohm's law, V equals IR. So R is the slope of these lines. And so we basically find the slope from the origin here to there, from here to that midpoint, and we average it. That kind of gives us the average resistance over this region. Now, why this region? Once we get below this, it's going to basically be turning off, and then we're getting a low voltage, and so then things start to propagate downstream. So this is kind of the critical discharging time where we want to start getting the output to go towards zero. It's not logically zero until it's here, but it gets towards zero. Again, digital voltages aren't purely digital. They're actually analog. They're switching and changing, but they end up in the binary states. Yeah.
What's the arrow from VDD to VDD half?
Oh, that's the switching, right? If you're starting here, it's going to discharge and kind of transition down to here. So yeah, so we average those two to come up with R on typically. Yeah, and then this is just saying the slope, right? R equals VDS over IDS. Now, let's swap this out. I'm going to do a demo now of K-layout. Wait. Oops. I can't see what I'm doing here, so I have to figure out how to get my there we go. Mirroring. Okay, let's turn this, close this. Okay, now we can all see the same thing. So first of all, if you can see here, I basically cloned the chip tutorials repository. This is the same website I gave to you with all the tutorials and everything. It's a GitHub site, and then I link it on. It's on my webpage with GitHub pages. You can see all the tutorials in here. If you go into, there's a K-layout directory. In this, it has a tech directory, which has all the SkyWater files. What are these files? Remember I talked about the layer colors, the stipple patterns, and things like that. It also has rules for doing the design rule checking in this subdirectory, layout versus schematic, and so on. This D25 is the 2.5D, the 3D view, so you can actually do the viewing. But again, remember I mentioned you have to have 3D acceleration compiled into K-layout. I don't know if they have that for all of the binaries on the K-layout website. You can also do stuff in Python. There's a Python interface to K-layout, so you can have it draw entire transistors and stuff. Now, what am I going to use in here? Well, I'm going to show you, for example, this is basically K-layout with a... now, if you don't put this tech directory in your home directory, according to the instructions, it won't be able to find it. there's a way to specify it on the command line, and that's in the tutorial. But I have it in my home directory too. And so you can just load a GDS file. Remember, this is the layout file format. And if I load this up, I get this. Actually, I will say you will not get this the first time you load it. What you will get is you will get, it's kind of ugly, but you will get this. Okay? The default background is white. And it's a mystery to figure out where the black is. You have to go to Find or File, Setup, Background down here under Display. And then in here you can basically choose black. So much easier to view, easier on the eyes. Again, you can change it to a different color. You can actually change all these colors over here. This is the default color palette. And I mentioned this if people have vision problems, color blindness, difficulty seeing things. These are the convention, but you can see the key and the value on the right of what layer it is. And that's why we talked about all these things, P-well, N-well. You have to know what the function of that layer is. But if I pick, for example, diffusion, diff, this is the diffusion area, which is going to be the source and drain of either it's going to be the area for either the PMOS or the NMOS. I can go in here and I can say, okay, I'm going to right select here. It helps to have a 3-button mouse or to know how to do right click. I know it's the tendency towards single button mouse pads. And Macs and stuff you can set up to be like region based, where on the right of my trackpad have it be right click, on the left be something else. Or often you can do like control click to do right click. It depends on your platform what you do. I usually use an external mouse, or ThinkPads have both buttons in addition to the trackpad. So I can go in here, and here's the things where you can do like the visibility modes. I can hide everything. I can show only the one that I selected right here. Or if I just double click, it turns it off and on, visibility. So I can actually go here and say show only selected. It turned off everything else. So this is the 2 transistor areas. And then I might want to turn on poly. So you can see that the PMOS is going to be on the top, the NMOS is going to be on the bottom. This is the layout I showed in the slide the other day. And then you see this kind of box in the middle here. This is also poly. But what happens is there's going to be a contact there to go up to metal. So that's why it's not just straight poly. So if we do that, we can kind of work our way up. Which one's P and which one's N? Well, that's going to depend on a couple things. We can turn on our N-well. Remember, this is a P-well substrate, and so we need to have an N-well that we put all of our P transistors in. So that's that green area. And then how do we, we could tell that this is a PMOS because it's there, but there's cases where you actually want to put, you may do some other things. So you can also then define the implant. So this PSDM is the P-type source drain implant, PSDM. And so you can see it drew this purple region around there, which will do the implanting for the source and drain of that transistor. And then, as you would guess, NSDM does the same thing, but down at the bottom for the NMOS device. Now, why is it bigger than the diffusion? Well, it can do the implanting everywhere, but you're going to have oxide over here that blocks it. Everywhere you don't have shapes on every layer is oxide. So this kind of defines this cut region. You have poly over it, and then you're going to do the implanting. It's only going to go into this region, essentially. Now, what do we want to show next? Let's then kind of work our way up. Again, there's some other layers like pin. That's an N-well pin. That actually doesn't do anything really. It just defines a use for the N-well, where if you wanted to make a connection to it, you'd probably do it in that pin. Or here's the label, which there isn't even a label there. This also has P-well pin and label, but there is no P-well drawing in this process. There's another implant here called HVTP. Many processes I mentioned in the 45 nanometer process last time you can have multiple different types of transistors. By drawing this HVT around this, that changes the threshold of the PMOS and says this is a high threshold voltage PMOS. So there's actually two PMOS types in this. This is a high threshold voltage. So I don't know what the VT is, but it's like 0.5 volts. And then if I didn't draw this, it would be like 0.4 volts. Why would I use different voltages or different thresholds?
Like your input-output devices, they require higher.
It could be your input-output devices. That's more the oxide, which often you'll see a thick or thin oxide, which is not here because it's not in this. But I said that you could increase the performance of a PMOS by increasing the width. Well, if I use low VT, that actually increases the current too. That's another option. But what we're going to find is that will actually make it leakier. And so we'll talk about power consumption. So it'll be faster, but then it will consume more power all the time. Yeah, question back there. Why is there no well for the bottom? That changes with every technology. You can see P-well pin and P-well label. Some might have a P-well drawing, but in this process, everything is P by default, and so they don't have you draw it. Some of them, even if it's a P-type wafer, will still have you draw it just because it's there. I don't know. So often you have to draw both of them. Or if you have technologies like a silicon on insulator where you don't have a substrate type, it's an insulator, you have to say what type of bulk you want for that transistor. So that'll change slightly between different technologies. Here you can see some of the contacts. So here's the metal 1 contacts. Actually, no, I don't want to do that one first. Here, I'll do this one first. This is the Li contact. Now again, there's 3 holes for the source and drain of the PMOS, and there's 2 holes for the source and drain of this. There's 1 hole here. Why do they do more than 1 hole for these? What do you think? There's a few reasons. Well, one was the design rules said they had to be exactly that size, right? So you can't make one this whole area, so you have to make it that size. So if you want to have more of it be through the layer, you have to copy them. Now, why would you want to have more of them then? Yeah.
Maybe to connect to multiple spots or for more current.
Yeah, more current. That's the reason. You can let more current go through there. Since these are very fine holes and they etch kind of delicately, sometimes they don't fully form. Like you might have this one that kind of half forms and it's only a hole like that. Or if it's partly obstructed, then it's going to end up having resistance and it's going to have poor performance. But if you have 2 of these, you have a redundant one. So it'll help with kind of your yield of the transistors and let more current go through by default. Yes?
So is the top one having more holes? Is that related to the thing you said earlier about the holes having more mobility?
So I'm talking about, when I talk about contacts and via holes, these are the vacancies of material where those are holes in terms of the particles. So no, that's actually not, but you can see that this is bigger than this. Remember, what is the width dimension? Or what is the length dimension? It's the direction the current flows. So it's going to go across like this and across like that. What is the width dimension? That's this way. The current goes that way. So you can see this one is this wide. That one is wider. It's not 3x wider. It's 2.5x, which is related to your question. Somewhere between 2 and 3 is kind of the best ratio. But it also depends on that ratio of the mobility of N to the mobility of P. So right there you can see that that is bigger for that reason. So these holes are all the same except these are to diffusion and these are to poly. Remember, when you look at the topology, the poly is on top of the silicon, so those are actually different depth holes. They're actually done with different etching processes and you have to tell it that. That's why you have this other layer that says, oh, that's it's called nitride poly, or NPC, nitride poly cut. It basically says, I want to etch that hole, or I want to connect to the poly. Actually, this is for a different reason, but it tells it that this is a poly contact. I'll even say the different reason. On top of this poly, you know how I mentioned there's many different steps and so on. this often isn't just poly. There's actually poly with this nitride layer on top that's kind of it makes it more conductive. So it's actually a sandwich of two conductors. And this says to cut through that top one to get to the poly. But that's besides the point. So this shape here says everything here goes to poly and these other ones go to diffusion. So that tells it how much etching it should do to make those contact holes. And then in this one, we have the Li layer, so this local interconnect. Not all technologies have Li. A lot of them I used didn't. It's more of an IBM thing, and Skywater uses it, but yeah, some of the other ones I didn't. A lot of them that don't have it, we'll just call this metal 1. And it's just kind of a naming scheme. But they call it Li because it's typically made out of a different type of material, which lets them make it smaller dimensions, but it's higher resistance. And you can see here, that metal kind of went over all these contact holes, and then we have the stripe down here for ground and a stripe at the top for VDD. And you can see this side is going to end up being the drain of this NMOS, where this is the source. This is going to end up being the drain of the PMOS, where the left is the source because it's connected to the VDD. And then you wire together these two outputs here to form the output of the inverter. Now,
Wait, so the right side of the NMOS is the drain or the source?
in this case, that's not always the case. It depends on the
It
usage.
kind of just depends on where it's connected to ground or the.
Yeah, it depends on the electrical connectivity. That's a good question. By the way, I could take this same layout, flip it horizontally, and it would have the same electrical behavior, right? Because these are symmetric devices and so on, but it's just written. I often find people putting inputs on the left and outputs on the right. It doesn't have to be that way. That just happens to be this way in this case. You could have your input to this gate be way over here, on the other side. Now, here we have the pins. I mentioned last time, this is where you like to connect to the Li with a router. So it's basically there to help routers. It says connect here to make a solid connection. And again, there's 2 points here to have multiple different options. Then we can go up through MCON. And there's only 6 of these, 3 up here and 3 down here. And then we have metal here. A stripe of metal on the bottom, metal 1, and a stripe of metal 2 on the top. Why? I mentioned Li is very resistive. If we end up putting these in rows later, this Li is going to be really long, and we're going to have a lot of resistance in our VDD and ground. So they do this thing here where they basically are double strapping it on 2 layers, Li and metal 1, with a bunch of these contacts between the two. It's like 2 parallel wires in 2 different layers. They're redundant, but they're there to improve the resistance. And then another nice thing is you can see usually a boundary of a cell. Now there's some other layers in here. Well, I mentioned the VT, but I'll skip over the other labels and stuff. Now, I think I gave you the same tech files, but there's this special menu if the tech file loaded correctly. eFabless was the company that was doing this open source stuff, and you see a menu here where you can run a bunch of things like, here's the 2.5D viewer. And then you can kind of do these rotations, right? And I can basically turn off some of these layers and so on. There's actually I had some bugs at one point, but you can see one of the interesting things is, I don't know how to zoom, there we go. Here's what I was talking about with, you have to know the difference between the P-type contact and the diffusion, because see, this one has to etch all the way down this deep, whereas this one only has to etch down that deep. So it's going to be 2 different etching steps because you want to do it less length, otherwise that one's going to start etching the poly. And so it's a timed thing. What else about this? I didn't draw the N-well. The N-well is not shown here. Oh no, it is. That is this shape, but the diffusion kind of bleeds into it. Those are the similar color. Yeah. Okay, let's load another example. So here's a PMOS gate, which you're going to have 3 NMOS, 3 PMOS. And you can actually start to see some of this where, again, you have the ground here. You see the ground's connected to this transistor right here. So this is going to be your lowest PMOS device. And then remember I talked about diffusion merging? So this green here, let me just turn off the layers. It's easier to view it without some of these layers. Oops. Yeah, so I'll just turn on the Li layer and the Li contact layer. So you can see that this, I had M1 on too. Let me turn off M1. And the M1 pin. So basically you have the ground here. You can see it goes up to here, and there's a contact here that goes down to this diffusion area. And then it is connected to this transistor. The other side of that is here. Notice there's no contact here. There's none of those. So this is Li that's going over that area, but it's electrically isolated. So the connection here in the green is only between this transistor and this transistor that connect. But I can't, if I turn off Li, you wouldn't see this, right? So that's why I'm leaving Li on, but there's none of those. So this transistor is in series with this transistor, and again, no contact over here to this transistor. Now, this is the top of that third transistor. So I have 3 NMOS transistors in series going up. And the connection's made with just the green here, not the Li. Now, the top transistor has 2 of these contacts here, and it's connected up to Li, and then gets routed back here and goes up to the PMOS devices. Because, right, we connected the top of the stack to the 3 PMOS in parallel. And let me turn off some of the layers in the top one. Turn off that HVT, turn off this layer. This is where turning off these things is useful. Even the NWEL, I know it's in an NWEL, I know it's PSDM, NSDM, right? And you can see here, so it goes through here, it connects to these 2 transistors by having these vias, these contacts. Again, I use contact and via interchangeably. They're just cuts that go between layers. These are technically the contacts are between the diffusion and the poly in the layer up, and then it's via everywhere else. So you see these contacts here up to Li, and it connects to this transistor on the left and this one on the right. The other side of this one connects to VDD. Now the one transistor on the right here, the other side of it connects to VDD too. So here's an example where you were asking me about the right side being the diffusion and the left side being, or the right side being the drain and the left side being the source. These 2 transistors are opposite. This one right here is the drain of this transistor and this transistor, but this side is the source of this transistor, and then this side is the source of this transistor. So they're flipped. They're perfectly symmetric in layout. The layout doesn't matter, it's how they're hooked up to VDD that determines that. And then we see this metal Li connection going across here and connecting to this other transistor, which the other side of it, so this is the drain of this transistor on the right, and then the source of it is the same as the source of this transistor over here. And so they're both connected to VDD. So you can see that one is in the same orientation as the one on the far left side, with the source on the left and the drain on the right. All right? I know it's kind of like, you're like, whoa, this is, but then you have the inputs here. So here's the input to this gate, or this poly is input A, let's say. Here's another input, and each of those goes up to Li down to the poly. And then if we add our metal on here, it's again just the power and ground. So all of the pin shapes are on this Li layer in here, here, and here. And then where's the output? Well, the output is this big shaped node here between the P and the N. Now we can also view this in 3D. kind of same idea. But you can see kind of the more complex metal shapes, right? Yeah, question back there.
Can the output connect to anywhere on that big shape if it were to go to
Yeah, that big shape is electrically the same, right? It can connect anywhere. Now, where will the tools connect? Well, that depends on the pin. And so where does it put the pins here? I have it turned off. We have LI pin. It'll actually connect there. Let me turn off everything else except, let me turn off diffusion, let me turn off poly. So here you can see for one of the inputs, it's going to connect to either of these two locations. For the output, it's actually going to connect to there. And then this other input, it has two locations, then another one, this is the other input here. Now, why is this in the middle? I don't know. Yeah, why didn't they put it over there? If you notice, when I talk about routing, most routers are on a grid. All of these are kind of spaced on a uniform grid. Notice that this one lines up with that one, and they line vertically. It makes it easier to route when they're on that grid. Okay. I think that's all I really wanted for that demo. So I'm going to go pop back to the lecture slides. We're not really running DRC and LVS on homework 2. I think that's going to be reserved for homework 3. I can't remember. I even took some of that out. I forget what I took out. I prepped all the homeworks back in December because I have 2 classes. So now I'm trying to remember what I put on each homework. All right. Yeah, so there's some stuff talking about those parameters that I already talked about. So the width, length, and R on. So again, width of 2 transistors, this is roughly 2x that, because this dimension. Almost every transistor for digital stuff is going to be drawn with the minimum length. Why? Well, it's easier to print with photolithography, and you generally don't want to make things slower. You want to make them faster. So why would you want to make it, if you made it a longer length, it would make it slower. So it's not only slower, but it's bigger. So that's a kind of a losing proposition. I will say analog people will sometimes do that because they actually want to control the resistance and use it in an analog circuit. So digital people, no. Analog people, yes. You can see a ruler here in K-layout. So 0.15, that's 150 nanometers or 0.15 microns. This is actually 1 nanometer, or 1 micron, or 1,000 nanometers. So this is 0.15, and this is 0.42 is the width of that. And again, it corresponds to the width and length in the current equations for the linear and the saturation region. Yes?
Is there a way on K-layout to see the measurements?
Yeah, there was a ruler at the top. You just click ruler, and then you do a click from here to here, and it shows that. Yeah. That's actually some questions I have you do on homework 2. I'm like, what's the width of this transistor? So, and then I talked about the R on and that stuff over there. So, now, I'll end with this. We have 10 more minutes, right? Yeah. There's one more kind of bonus terminal on a transistor. I've talked about the source drain gate. They actually have a body connection too. What is the body connection? Well, it's the substrate. Or if it's in a well, it's the well. So if I have a PMOS and an N well, the connection to the N well is this body of the transistor. And it's frequently drawn like this, out from the center here. It's kind of overlapping, crude drawing. And what can you do with that? Well, when you do this, you can change the voltage on the P substrate. Now, how do you do that? Well, you connect to it with P plus type. Why? P plus to P connects. They're both the same type. So this is also called an ohmic contact for some reasons. So it's a connection. In this case, we're connecting it to the source of that transistor, which will be ground. That's the common case for NMOS. The P is usually connected to ground. It doesn't have to be. What happens if I change the voltage on that body? Well, remember, this goes back to the diodes at the very beginning. I have P and I have the N type for the source and the drain. What happens if I add a positive voltage? Let's say it's not connected to the source here. So let's say I disconnect this, and I add a little bit small voltage here, plus small voltage. Well, what happens? So I have two diodes. Remember, I have a diode that's essentially, let me change the color, right here. I have another diode right here. Now, let's look at the one on the left. Well, let's assume the source is ground. If I have a small voltage there and a ground voltage there, I have a diode with a slight forward bias. If I make that too big, what happens? Well, suddenly I have current going through that from the substrate to the source. That's bad. So you can't raise that too much. Same thing would happen over on the drain side, if I had, depending on the voltage on the drain. Now, but what happens in that region between turning on the diode and not? Now remember, we have that depletion region in the middle of the diode. Well, if I do that, you're going to essentially modulate this depletion region here, and you're going to change how many electrons and holes are in that region. And then what that does is when you change the number of those, you change the amount of voltage you need on the gate to form the channel. What does that do? That changes the threshold. So you can apply a small voltage there, and it will actually decrease the threshold voltage. So normally, if it's fixed at a voltage, you're stuck with the threshold voltage depending on the concentration of the P substrate dopants. Now you can electrically control it. People do this for low power usually. If you apply a negative voltage there, it actually makes that depletion region bigger and does the opposite. It makes it harder to turn on the transistor. So frequently when people want to go in low power mode, what do? They apply a negative voltage on the bulk and say, put it to sleep, turn everything extra off, and now it'll consume less power. And so that's kind of the extra thing. So it's frequently used in techniques for low power. But by default, you would want to connect this one, the P-type to ground for the NMOS, and then the N-wells get connected up to VDD for the PMOS devices. Because remember, it's dual. PMOS and NMOS are opposites. And you can do this. Now, with NMOS, there's one substrate usually in a bulk technology, so they all share the same substrate. But the PMOS devices can each be in their own N-well. So you can bias each of those N-wells differently. Or you can put a bunch of transistors in one N-well and bias them all the same. And it does the same thing. Now, so I'll leave that at that. Now, the thing I'm going to kind of skip over a bit is the CMOS stuff. I will say, you've seen this in CSE 12, you've seen this in CSE 100. You know that even with just switch logic, the pull-down network and the pull-up network are dual networks of each other. So they are mutually exclusive, meaning that only one of them has a connection between ground and the power supply. If there's a connection in both of them, that's a problem. It's not static CMOS. And then the general behavior of this is you use parallel and series combinations. So if you put two transistors in series, in this case A and B with NMOS devices, it's essentially an AND operation. A and B both have to be on to have both switches closed to have a connection. And then if they're in parallel, either A or B can be on to have a connection, because then one of them will connect and the other one may or may not connect. Now, the only And then same idea applies for PMOS devices, except the gate terminal of PMOS is opposite. So a low voltage means the switch is closed, and a high voltage means the switch is open. But series and parallel still are both the same thing. Now, what do I want to say is important? Now, why PMOS and NMOS? And why PMOS in the pull-up and why NMOS in the pull-down? You know, someone might ask, well, why don't we just have NMOS in all of them? They're faster, right? So why not always use NMOS? Well, the reason is the noise margins. If you want the output of your gate to be VDD, you have to use a PMOS, because if you put an NMOS in the pull-up network, it's going to pull the output all the way up to VDD minus VTH and then shut off. And it's not going to be able to pull it up because the voltage, I can draw it in kind of a quick connection. Let's say we have 5 volts here in NMOS, and we have 5 volts here, and let's say our VTH of this is 0.7. Now and let's say this starts out at 0 volts. Well, what's going to happen is it's going to charge up to 4.3 volts. And then what happens at 4.3 volts? This is VG. This is VS. VGS is now, what? 0.7 volts, which is about equal to VTH. I've pulled it up to the point that it's now not greater than the threshold voltage. This transistor is on the brink of turning off. So it can't pull up to 5 volts. So that means if I had a logic gate and I wanted to have NMOS in the pull-up, I would never have an output voltage equal to VDD. It'd always be VDD minus a threshold. Well, now what would happen then if you cascade that? If that fed to another gate, let's have another case now where the next stage, this feeds out, and now this is 4.3 volts on the gate. This is 5 volts here. What can this one pull up to? It can pull up to 4.3 minus 0.7 volts. It'll be 3.6 volts on the output of this one. So every stage of the logic that had these NMOS in the pull-up would lose voltage, and I wouldn't be able to use it, right? So that's why we say strong and weak. It's really this effect.
So is the 5 volts on the top, is that the VDS, and then you're subtracting minus the...
Yeah, that's like VDD or VDS. VDS of this would start out at 5 volts because this is 0, and VDS would go down to 0.7 volts. But the thing that dominates is the VGS, which first determines is it on or off. Because remember, VDS just determines is it in linear mode or saturation mode. So the first question is always, is it on? Check VGS. Now check the relation of VGS and VDS to find out which mode it's in. So yeah, it actually would sweep through both modes of linear and saturation while it's charging this up. You know, I was talking about the charging effect. So it'd kind of charge up and be in saturation, then go down into linear mode, and then shut off. So, all right, I think that's a good place to leave off. You know, there's the other stuff for CMOS logic, which I'm not going to talk about. And I already did an example. Here's another Skywater gate that you could go look at. And you'll also do this on the homework. So. Hey. Yeah.
So when I was reading the textbook, all the equations that you showed, they referenced that the model they used was a long channel.
Yep.
Is that what this was for?
Yeah. So what that means is this doesn't work when you get below like 65 nanometer.
I see.
And the saturation effect actually becomes more significant.
Are we going to talk about short channel?
No.
Okay, so it was just all long.
Yep. You should, it's good to know. Like this is something you get into in a devices class where you start to talk about that. And, yeah.
Okay, that makes sense.
Yeah, more circuits than VLSI digital design. Yeah.
So I'm trying to do the homework again with the links.
Yeah.
And I was just curious because